In this example, I'll go through analysis of variance for the completely randomized design, also known as one-way analysis of variance. So with this example, we have employees trying to assemble a filtration system using three different methods, method A, B, and C. And the numbers, the variable that we'll analyze, are the mean number of units produced per week using each method. And we have 5 measurements for each method. The sample mean for the first method is 62 with a standard deviation of 5.244. A mean of 66 for the second method, so more units produced using the second method, and a standard deviation of 5.148. And for the third method, far fewer units produced using the third method, mean of 52 and a standard deviation of 5.568. The overall mean is 60 for all 15 measurements. So the way that analysis of variance works is it's best to think about it as numbers in an analysis of variance table. And we'll start off with this column in the table, which is the sums of squares. And the treatment sum of squares, the formula for that is to look at the differences between each of the treatment group sample means. So for example, group 1 for method A, 62. Look at the difference between that and the overall mean, 60. Square that difference, and then multiply by the sample size in that group. And then do the same thing for each of the other two groups. So 66 minus 60 squared and multiplied by the sample size, and then 52 minus 60 squared and multiplied by the sample size. And if we add those three numbers together, we get 520. So that's the sum of squares due to treatments. The error sum of squares, for that, we look at the standard deviations within each group. So for example, for the first group, we square that standard deviation and multiply by the sample size minus 1. And then for the second group, we square that standard deviation and multiply by 5 minus 1. And for the third group, square that standard deviation and multiply by 5 minus 1. And then we add those three numbers together, and we get 340. So that's the sum of squares column in the ANOVA table. In the degrees of freedom column, the treatment degrees of freedom is equal to the number of treatments minus 1. So 3 minus 1 in this case, or 2. And then it's easier actually to think about the total degrees of freedom first. The total degrees of freedom is just the total sample size, 15 minus 1. And then the error degrees of freedom is the difference between the total degrees of freedom and the treatment degree of freedom. And I didn't mention the total sum of squares is the sum of the treatment sum of squares and the error sum of squares. The mean square column, this column here, is the sum of squares divided by its degrees of freedom. Okay, so 520 divided by 2 comes to 260. 340 divided by 12 comes to 28.33. And then the F statistic is the ratio of the mean squares. So 260 divided by 28.33. So that's 9.18. And the idea here is that if there's no difference in the treatment means, in the means in each treatment group, then these two numbers ought to be close to each other. If there is a difference, then this mean square will be much bigger than this mean square. And so this ratio, if it's quite large, that indicates that there's a difference in the means between the three treatment groups. So to assess how large it has to be, we calculate a p-value, and for that we use an F distribution. And an F distribution has 2 degrees of freedom numbers associated with it. One's called the numerator degrees of freedom, which is 2 in this case. It's equal to the treatment degree of freedom, because it's in the numerator of the F statistic. And then the denominator degrees of freedom is the error degrees of freedom, 12. That's because that appears in the denominator of the F statistic. So if we put all that together and find the tail area to the right of the test statistic, 9.18, for a F distribution with 2 numerator degrees of freedom and 12 denominator degrees of freedom, we get the p-value 0.004. And then the decision rule, as usual, set a significance level and reject the null if that p-value is smaller than the significance level. So 0.004, smaller than 0.05, so we reject the null hypothesis in favor of the alternative. The null hypothesis here says that the 3 treatment means are the same, and the alternative hypothesis says that the 3 treatment means are not all the same. So in this case, we're rejecting the null and concluding that the treatment means are not all the same for each of the methods. The other way we could do this is using a critical value from an F distribution. And we use an F distribution with 2 numerator degrees of freedom and 12 denominator degrees of freedom. And the value of F such that the significance level 0.05 is in the upper tail would be 3.885. And if the F statistic is in the rejection region above this value, then we would reject the null hypothesis. So we do in this case. So let's see how XLStat handles this. So this test is to be found under modeling data. So modeling data and then ANOVA, standing for analysis of variance. And we pick the quantitative variable, which is the scores. Well, it's not the scores in this case, it's the number of units. I'll change that label in a second. The qualitative variable is the location. That's why I'm confused. I'm looking at the wrong data set. Let's go back to this one. Okay, there we go. Units is our variable, is our dependent variable, y. Our qualitative variable is method. There we go, that makes a lot more sense. Okay, and then there's various options we could pick here, but I'll just leave everything at the default settings. We'll click OK, and we're going to get lots of output here, but the only thing that we're going to concentrate on is the analysis of variance table. Okay, so it's all this stuff we're not going to worry about. We're going to worry about this table here. Okay, so this is the analysis of variance table. And it's the same as we calculated by hand. So here's the degrees of freedom. Here's the sums of squares. Here's the mean squares. Here's the F statistic. And here's the p-value. Okay, let's look at another example. This is for a company with 3 different branches. 3 different plants, 3 different manufacturing plants. And the employees, looks like they took an examination, and 6 employees from Atlanta, those were their scores. These are the employees from Dallas, and these are the employees from Seattle. So as before, Sample size for Atlanta, sample mean, sample standard deviation. For Dallas, sample size, mean, and standard deviation. And then for Seattle, sample mean, sample size, sample mean, sample standard deviation. And this is the overall mean, 73. Sums of squares. Again, we can calculate the treatment sum of squares by looking at the differences between the within treatment sample mean and the overall mean, squaring those differences and weighting them by the sample sizes. And then the error sum of squares is looking at the within treatment group standard deviations, squaring those and weighting them and adding them up. And then the total sum of squares is the sum of those two. And then the degrees of freedom, well, we've got three groups in this example too. So degrees of freedom is 3 minus 1 or 2. Total sum of squares is 18 minus 1, which comes to 17. And then the error sum of squares is the difference between 17 and 2. Mean square for treatment is 516 divided by 2. For error, it's 430 divided by 15. And then the ratio of those two, 258 divided by 28.67 comes to 9. The F distribution with 2 numerator degrees of freedom and 15 denominator degrees of freedom has an upper tail area to the right of 9 that comes to 0.003. It's smaller than alpha, so we reject the null hypothesis and conclude that the treatment means are different. There's the critical value in case we wanted to use that method for making the decision. The test statistic is inside the rejection region. It's bigger than 3.682, so we reject the null hypothesis. And let's have Excel stat do the analysis to check our numbers. So we'll pick our data. Make sure we get the right spreadsheet, so this one. And then the qualitative variable tells us which location. And then okay that. And we're looking for the analysis of variance table. Give me a second now. Okay, and then we'll scroll down, and here's the analysis of variance table. There's the degrees of freedom, sums of squares, mean squares, F statistic, p-value. So it all matches up with what we calculated by hand. So that's one-way analysis of variance.